Howdy guys, I'm going to run you through a quick example here of another equilibrium problem so that you can practice at home before you take the quiz tomorrow. Okay, so here we have a situation. We have a hemispherical sign that's 1 meter in diameter and of uniform mass density, and it's supported by 2 strings as shown here. So the first string is located on the edge of the sign, and the other string is located about 3/4 of the way across the sign. Okay, the first part asks to draw and label a free body diagram. So I'll start here and I'll draw my sign here, and then I'm going to label all of the forces that are acting on the sign. So I have here the tension of this first string, and then about 3/4 of the way through I have the tension of the second string. And then I of course have the weight of the sign, which, since it's of uniform mass density, acts right smack dab in the middle of the sign, like that. Okay, now I'm going to put in my lengths here too. I might as well, because this is acting in the middle of the sign, the weight. I know that this length from here to here is going to be 0.75 meters. I'm sorry, it's 1/2 of a meter from here to here, and we know from here to here was 0.75, so that means that this distance from here to here is 0.25 meters, and over the edge here is 0.25 meters as well. Okay, so I have everything labeled here. Let's move on to the next question. What are the conditions of equilibrium? So just like we did way back in the beginning of this year, we want to think about what's going on in this situation. Okay, is the sign moving? It is absolutely not moving, so that means it is in equilibrium. It means all the forces in the x direction add up to 0, and all the forces in the y direction add up to 0. So there's actually no forces in the x direction, but we'll leave that as, so we don't have to worry about any forces here. Okay, now the forces in the y direction also equal 0, but we have 3 of them acting. We have T1, T2, and the weight of the sign. T1 and T2 are pointing up, so they are positive. So we have T1 plus T2, and the weight of the sign is pulling down, so it is going to be negative. And those again equal 0. So I can rearrange this to say that T1 plus T2 is equal to the weight of the sign. Okay, there's our forces. Now let's think about the torque. Since it's not rotating, we know that the sum of all the torques is equal to 0. Okay, and we can have torque that is in the counterclockwise direction, and we can have torque that is in the clockwise direction, and those two must cancel each other out. So we know that the torque in the counterclockwise direction, which is positive, minus the torque in the clockwise direction has to equal 0. Or the torque in the counterclockwise position equals the torque in the clockwise position. Okay. Those are my conditions of equilibrium. Part 3 says, if the sign has a mass of 6 kilograms, what's the tension in each string? Okay, so this is where I'm going to start solving for stuff. So I'm going to start by writing down what I know. I know that the mass of the sign is equal to 6.0 kilograms. I know that the length of the sign is equal to 1.0 meters. I know that, well, I can figure out the weight of the sign, because the weight of the sign is just its mass times a gravitational constant, so that's 6.0 times 9.8, and that equals 58.8 newtons. Okay, And I think that's about all that I know that's going on here. Okay, so let's look, oh, and we want to solve T1 equals question mark and T2 equals question mark. This is what we're looking for. Okay? So I look to my conditions of equilibrium to see if I can find what these values equal. So looking up here at my forces, I see that T1 plus T2 equals the weight of the sign. I have the weight of the sign, but I still have two unknowns, so I'm going to have to come and use the condition of the torque being in equilibrium to find those values. Okay, so to solve those, the first thing I'm going to do when I consider torque is choose a pivot point. And I'm going to choose this point right here, right where T1 is, to be my pivot point. Okay? Now by doing that, T1 effectively has no torque because the lever arm is 0. Alright? But my other forces, T2 and the weight of the sign, still could provide a torque. So looking at T2, I see that T2 would be pulling the sign in a counterclockwise rotation. So it produces a counterclockwise torque. T2 produces a counterclockwise torque. And I know that the torque of T2 is going to equal the tension of the second wire times the length of the lever arm. And the length of the lever arm here, again, it was located 0.75 meters or 3/4 of a meter from the edge of the sign here. So it would be 3/4 of the length of the sign. Okay? Now the weight of the sign also produces a torque. In which direction does it pull? Well, it pulls the sign in a clockwise direction. So it produces torque in the clockwise direction. Okay? So the torque from the sign is equal to the weight of the sign times the length of its lever arm, and its weight acts halfway through the sign, so it's going to be 1/2 times the length of the sign. Now I can substitute values in here if I want to. I'm not going to do that just yet. I'm going to go on and look at my equilibrium of torque. I'm just rewriting what I wrote up there. Counterclockwise minus the sum of the torque in the clockwise direction, and that equals 0. Okay, so I have no other torques that are acting here. I know from my equilibrium equation here that the torque from T2 is going to equal the torque of the sign. So I'm just going to set those bad boys equal to each other. We'll say this is the torque of T2 equals the torque of the sign. Okay, now I'll just take my values here and substitute them in down here. So tension 2 times 3/4 of L is equal to the weight of the sign times L over 2. I'm trying to find T2, so let's go and multiply each side by 4 over 3L. And we see over here that our L's cancel out, and this goes to 2. So T2 equals 2/3 the weight of the sine. I found my weight of the sine to be 58.8 newtons, so I'm just going to substitute that in. And that works out to be 39.2 newtons. So T2 equals, oh, and if I'm thinking sig figs, it'll just be 39 newtons for T2. Right? Now I still have to find T1. Well, I'm going to come back up here and use this equation to help me find T1. So I'll do this in purple here, right next to T2. I knew that T1 plus T2 equals the weight of the sine. T1 equals, rearranging, the weight of the sine minus T2. So T1 equals, we said 58.8 newtons minus T2, which was 39.2 newtons. So T1 is going to equal 19.6 newtons, which, if I'm using sig figs, which I should, T1 is going to equal 20 newtons. Okay? And there you have it. You've solved for those unknowns. I hope that helps, and I hope you can use this to help you work through some other problems.